Assalamualaikum. We from Group 3 will present about nuclear logging tool for formation and reservoir technology BTO3114. My name is Zulhairi Bizkipi, PH18027. My group member are Muhammad Aminuddin bin Muhammad Syukuddin, PH18030, and Muhammad Hafiz bin Hassan, PH18040, and Muhammad Nur Izzat bin Abdul Majid, PH18009. Introduction. Well, logging is one of the most important use of nuclear physics in the petroleum business. Log analysis purpose is to map out the downhole value of reservoir properties such as porosity, fluid saturation, and permeability. Well, logging usually used two forms of radiation, which is gamma ray and neutron ray. Basic principle of nuclear physics apply to borehole logging. Nuclear physics is the branch of physics that examines atomic nuclei, their constituent and interaction. Well, logging is the activity of creating a thorough record of the geological strata penetrated by a borehole. The log can be based on visual inspection of sample brought to the surface or physical measurement taken with instrument lower into the hole. Geophysical well log can be performed at any stage of a well cycle. The particle of photon penetrating capability allow them to be detected through casing and annular material, and they can be employed independently of the type of liquid in the borehole. Next is formation density tool principle and its application. Formation density tool. A gamma ray source is used to irradiate the borehole wall in a formation density log. The reflected rays are then recorded by a gamma ray counter. The formation density log determines the formation bulk density. Its primary purpose is to calculate the formation total porosity. It can also be used to locate gas-bearing deposit and distinguish between evaporates. Its principle is a radioactive source and detector are dropped down the borehole, and the source emits medium energy gamma ray into the formation, making it an active nuclear tool in an interaction known as Compton scattering. This gamma ray interact with electron in the formation and scatter. The formation attenuates the gamma ray flux that reach each of the two detectors, and the amount of attenuation is determined by the density of electron in the formation. A formation with high bulk density also has high electron density. It considerably reduces gamma ray, resulting in a low gamma ray count rate at the sensor. Formation with low bulk density is low electron density. It attenuates gamma ray less than high density formation. Hence, the sensor records a greater gamma ray count rate. The electron number density is a quantity that describes the density of electron in a formation. Number density is directly related to bulk density for a pure substance, and we may derive the relationship in the following way, which is Ne equal to Nz over A times by Pb, which is Ne is the number of density of electron in the substance, N is Avogadro number, Z atomic number, A atomic weight, and Pb is the bulk density of the material. For its application, because the density of sandstone and limestone is well known, this approach is the most dependable porosity indicator. Its primary purpose is to estimate the formation total porosity. It can be used to locate gas-bearing deposit and distinguish between evaporates. One of the greatest techniques to detect lithology in a borehole is to combine formation density log data with neutron log data. Next is the photoelectric factor key and lithology indicator. The photoelectric factor It is used as a guide to lithology identification, together with the gamma ray, neutron, and density porosity curve. Atomic number whose aggregate composition in the formation determine the photoelectric factor response. The photoelectric index is an additional measurement used by most recent generation of density logging tool that record the absorption of low energy gamma ray by the formation in band per electron. The index is a better indication of mineralogy than either the neutron or density because the results are less sensitive to the pore volume fluctuation. When used in a conjunction, the neutron density porosity overlay as an additional input. The photoelectric index log can help resolve mix of minerals such as leucine in complex carbonates such as salty dolomitic limestone and anhydritic dolomites. The placement of the neutron porosity trace must be evaluated concurrently with the photon electric curve for successful interpretation because the photoelectric factor curve has a finer vertical resolution than neutron curve. It should be close monitored. As a result, in feedback where average effect is adjacent feedback may smooth the neutron and the CT respond unfavorably. The PE character can provide a better reading on lithology. As we can see the photo down here. Okay. Next is a graph key lithology indicator. The visual examination of drill cutting can be utilized to transcribe lithology from log into standard lithology symbol that are used in the graphic log that we can see on the right side of the slide. Next is hydrogen index, neutron tool, principle and application. Neutron log is mostly affected by the number of hydrogen atoms present in a formation. Its primary application is in determining the porosity of a formation. The gadget works by delivering high-energy neutrons to the formation. In the creation, the neutrons scatter, losing energy, and release high-energy gamma ray. The scattering reactions are most efficient when hydrogen atoms are present. The low-energy neutron or gamma ray that result can be measured or their count rate is proportional to the number of hydrogen atoms in the formation. The neutrons are slow and absorb very quickly and over short distance in formation with a lot of hydrogen atoms. The gadget has a poor count rate of slow neutron or capture gamma ray. As a result, in high porosity rock area, the count rate will be low. For its application, first is porosity determination. The main use of the neutron log is to provide porosity information. The tool is sensitive to the amount of hydrogen in the formation and to a less extent upon other elements. It is assumed that the contribution to the measurement by element other than hydrogen is negligible and that the contribution to the measurement from hydrogen come entirely from the fluid fully occupying the pore space. Second is lithology identification. The direct use of the neutron log to identify lithologies depend upon the recognition of which lithology may contain the hydrogen atom. Next, I will pass my presentation to Aimanuddin.
Hi, I am Imanuddin, and I will proceed with the hydrogen index and determination of porosity using neutron and density logging. So first off is hydrogen index. Hydrogen index is mainly used in neutron logging, whereby it utilizes a neutron source to measure index in a reservoir. So because why hydrogen index is used is because hydrogen, as known, to be a primary element of both water and hydrocarbons. The process of neutron logging, it would be when neutrons hit the hydrogen atoms in a formation, they lose their maximum energy, slow down, and eventually reach a low energy or thermal state. The hydrogen index is then transformed to neutron porosity using neutron porosity instruments. So basically, this hydrogen index is a reference to the is a reference to the is a reference in porosity logging, and we move straight to the uh, determination of porosity using density and neutron log. But before we go through that, we're going to look at what is density log. The the same concept as neutron logging, whereby the emission of atoms and energy is released and the data is acquired. But for density logging, instead of using neutron atoms, it uses gamma rays. So as you can see here, after multiple collisions with electrons in the formation, the gamma rays lose energy and scatter. The same concept with neutron logging. The number of collisions is proportional to the electron density, in which the number of electrons per unit volume. For density log, porosity is inversely proportional to the density of the rock in general. So we go through to determine the porosity using the combination of these two logs. The physical properties of fluids and rocks are well defined by porosity tools, and the shale effect and the neutron density gas effect are two of the most well-known examples of tool reactions. I'm gonna go through those two later on the next slide. Okay, wait. So the first reaction between these two logs is the shale effect. So the neutron, as you can see for the image here, the red one is the neutron log, the blue one is the density log. As for the shale effect, the neutron porosity measurement is higher than the density porosity when under the shale effect. It's because the neutron's reaction to the shale's huge volume of fluid is absorbed, and it produces gap between the density and neutron porosity curves in shales, known as the shale effect. This is where you determine the shale effect when you combine these two logs. And then the second one is the gas effect, where the neutron porosity tool detects gas field porosity as low porosity. Density and neutron porosity curves are neither overlapping nor separated from one another. So this, as you can see, this gas, oil, and water are under the gas effect, and the reason why density log is higher than the neutron log is because density porosity is smaller than density porosity, giving rise to the phrase crossover. So the simple way to read this is when you see uh, the reverse crossover between the normal log. That is where the gas effect takes place. When you see a huge gap between the huge gap or huge change between the two logs, it would be the shale effect of the logs. So that's all from me. We'll move on to the next presenter. Thank you.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Hafiz bin Hassan and I will continue about this presentation. Okay, about our nuclear logging process. Porosity, for my part, porosity compatible scales and density neutron crossover is a logging device that is a contact tool that emits a gamma ray from a source. This gamma ray was emitted and collided with the formation electron and scattered around the planet. And the porosity will be determined by the number of the returning gamma rays in the indicator of formation bulk density. Formation bulk density measured by the log must be corrected for Bohr irregularities. Convert bulk density to porous using chats in a log interpretation chatbot. So next, continue to construct the computable scale or chatter chatter box. We need to follow the following step. There is one. For the first step is the limestone will be 0% porosity with the density log width to a constant that is 2.71 gram per centimeter cubic, and the neutron log reaches to 0. And the second step is for the limestone with 100% porosity, and the density of the log reaches at 1 gram per meter cubic, and the neutron log reaches to 100. Okay, when the density neutron log in combination log that is simultaneously records neutron and density porosity. In some zones, the porosity are recorded in the logs differ by three reasons. That is, the first one is the metric of density used by the logging program to calculate porosity is different from the actual formation metric density. Gas is presented in the formation pore space, and the shell or clay is presented in a formation. Okay, next this the 2 point that the 2 point can be plotted in a graph of the density on the log y axis against neutron velocity from the x-axis on the log of the x-axis is here plotted on the graph. For the cross plot for density and neutron logs plotted in a compatible scale, there will be a separation of the density and the neutron logs for sandstone and dolomite, but no separation for limestone. And the density neutron cross plot analysis can be ambiguous when the formation is mixed with mineralogies such as sandstone, dolomite, and limestone. Next is the LWD nuclear logging. The analysis for LWD reading is done while the instruments are operating in the borehole is being dug. The gadget utilized in this application must be withstand extreme temperature and shock and vibration. For rapid sampling, the stats technique are applied to rapid sample, taking on incoming gamma count. So ultrasonic caliper are another method of obtaining density in enlarged boreholes, such as a constant measurement of standoff using a series of ultrasonic calipers.
Assalamualaikum warahmatullahi wabarakatuh. Thank you to Hafiz. Okay, in my part, I want to share about the lithology determination on a simple case. Okay, in our case study, we choose the phases interpretation of Goro formation in a Zindapi structure, and the stand for that Central Indus Basin, Pakistan. Okay, there are three types of lithophases. Is identified on the basis of mutlaq, wireline locomotive, and a regional study in a Zindapi ethic line. Okay, there are two wells that we choose in our case study is the Zindapir X1 and well X1 that are used for study, which are the drill in the Zindapir structure and the Sulaiman Fort Bed and Central Indus Basin, Pakistan. Okay, in this part, in the picture below was show the essential basis of the understanding the link depositional environment is the morphology of the marine environment from the beach to shelf edge to a continental slope, and the fine grained sediment are found in the deeper parts of the ocean, while the coarse sediment are found in the shallow part. Okay, in this table will show the direct correlation between the facies and a variety of other log shape in relation to a sedimentological relationship. A geophysical well log study on the paleo environments of the hydrocarbon production zone in the Ichungchi formation. Okay, in this picture will show the facies interpretation of Koru formation in the Zindapil ones and well X1. Will show the correlation between the GR lithofacies scale of a Y-line log with a coloring scheme that was given. Okay, in the next part is a calibration and a log quality control parameter. Okay, the gamma ray enter the formation and undergo the Commission scattering by the interaction with the electron in the atom composing the formation. The Compton scattering reduce the energy of the gamma ray in a stepwise manner and scatter the gamma ray in all directions. Okay, the formation with a high bulk density has a high number density of electron and it attenuates the gamma ray significantly, and hence a low gamma ray count the rate recorded at the sensor. Okay, a formation with a low bulk density has a low number density of electron. It penetrates the gamma ray less than the high density formation, and hence a higher gamma ray count rate is recorded at the sensor. So the bulk density of the rock is determined by the solid mineral that makes up. It is porosity, the density of the fluid that will fill those porosities. As the result, the formation density tool can be used to determine the porosity, locate a low density fluid or gas in a pores, and add a lithological identification. It is because the electron number density and bulk density have a direct relationship and no collaboration is required. So the tool is to calibrate by placing it in a block of poor limestone that soaked with a fresh water or precisely specific density. Okay, this is the table will show the atomic number and mass data they are used to calculate the electron number density and bulk density. This is a type of element that are commonly found in the crust. As you can see in the picture, will show the formation density tool mineral correlation plot. Okay, the formation density tool mineral correlation plot is the indication of assay performance in a validated analytical range, including the regression model, a slope of the line and width, and a correlation coefficient. Okay, as you can see in the picture, will show the density that some formations such as a hydride, a sulfide, and a halide must be corrected. So the reading in the gear bearing formation was shown in the picture at the first picture will show the correction that need to make. Okay, and then the correction also need to be made in the borehole is larger than 10 inches in diameter. So the correction curve of the tool is shown in the second picture. Okay, I think that's all for me. Thank you.